Good afternoon, all. Welcome to the track of malware analysis. We have a lot of papers, so I think that it's better we start soon. Each presenter has 15 minutes, and then we have the time for a couple of questions. So the first paper is entitled Towards an Automated Pipeline for Malware Detection and Classification Through Machine Learning.
Thank you. Thank you, everybody. Thanks for joining, and it's a pleasure to be here. So we will talk, as said, about a machine learning-based pipeline for malware detection and classification. This is the result of the master thesis work of Nicola, student here in Torino, in collaboration with me and Daniele Ucci at ITASEC Technology Consulting in the cybersecurity division. So, okay, so we are interested in malware taxonomy. So what we want to do is a preliminary work where we want to provide a framework to help analysts in first inspection of a suspicious sample. The idea is the pipeline depicted here, that we described in more detail, takes as input a sample and goes through a first stage of detection. Of course, we want to be able to distinguish between malicious and not malicious software. And in case it's considered malicious, it goes through 3 other stages, where in each stage we try to classify the malware according to their main characteristics. In type, that is the major groups of virus, ransomware, greyware, and so on. Going into a deeper detail, we want to classify it by family, so a finer classification of the type, and at least the main behavior that characterizes this sample. We will describe the last stage, or the quarantine stage, in a moment. So, as always in the case of machine learning-based analysis, the first issue we have to consider is the data. We have to get data to fit the algorithm and to train the model. And of course, we need labels. We want to, of course, be able to validate our model, and we want to be to use a supervised approach. So we need this data to be labeled. For the first thing, we used an open source dataset, the Ember dataset, that was in the 2018 version. And of course, I don't have time to go into the details of the dataset, but you can find all the details in the official repository. It consists of 1 million portable executable files that are already preprocessed in a semi-raw static fashion. So in this work, we will be dealing with static analysis with all the limitation that it carries, but it was our starting point. For the labels, we considered a tool, open source, AV Class 2, that is the second version that was released around 2019. And how does it work? When you query a tool such as VirusTotal, it returns around 70 antivirus engine results for each sample. And in case the sample is classified as malicious, AV class go through the results of each of these engines, and substantially it tries to parse the name of the result, since we know that we don't have a standardized, unique nomenclature for all the antiviruses. It tries to extract keywords in the name returned by each engine and tries to map it in a common taxonomy table that it has built in, and in case it's customizable. So we can see an example of the outputs for 2 samples. For the first case, this sample is classified as malicious by 33 out of 70 antiviruses. 10 of them classified it as a grayware or grayware adware. 8 of them classified it as in the alt rotator family. So we can see already that we have to be careful here, since it's intrinsically a multi-label problem. But for the time being, we considered, let's say, a majority vote approach. So we consider only the most frequent class for each category, wherever variable. So for the type, the behavior, and the family. For the features, okay, we already said that are all static analysis-based features, and we don't have the time, but are more or less the same features that are provided by the Ember developers as a benchmark model, and are divided into 8 major groups, are more or less standard static features, so nothing too fancy, was just a starting point to see the capability of this approach. We just did a slight modification on the import function because we wanted to avoid the hashing trick in order to avoid losing information when compressing with the hashing. But for the rest, it's the same features that can be found detailed in the documentation in the paper in Ember. So, as we already said, the model takes as input the samples, and for each stage of the pipeline, we train a single light gradient boosting machine that is a decision tree kind of algorithm. And if the quarantine stage, the last one, is added in order, because actually we know that, for example, the detection stage is not perfect, is not infallible. So there could be some inconsistencies between different stages. For example, a sample classified as malicious in the first stage could be classified as benign in some other stages. In this case, in case of these kind of inconsistencies, we put the samples in the quarantine stage, and we trained a different model, a different detection model for the quarantine samples. This was in order to try to recover some misclassification errors in the previous stages, and also to rise at least the overall detection rate of the pipeline. Okay, so the results are numerical results of the performances are actually kind of difficult to discuss because actually we didn't find in the literature an approach, a unified approach for the complete classification of the malware like we did here. So, but anyway, we can see that, for example, in the detection rate, in the detection stage, the results are comparable, are not optimal, are comparable with the state of the art. For the other stages, due also to the reduction in the number of samples for training, for the other stages, the results are good, but can be improved. But as I was saying, this is not the point. We were more interested in this case in exploring the possibility of such a pipeline and the robustness of the same set of future vectors in going through all the stages of the pipeline. So, just a comment on, we used the light gradient boosting machine also because since it's based on decision trees, it's easy to recover the relative future importance in the classification. So while in the detection and the classification stages, we have substantially no surprises in what we can see in the literature so far. So we see the size, the V size, the virtual size, the timestamp. So nothing too surprising. It's quite standard as a result. But what's interesting is that the most important features in the quarantine stages are all related to the byte entropy, the byte histogram, and the printable strings distribution. And since this is known, these features are known to be related often to cases in which some sort of packing or obfuscation are present, this could suggest that the misclassification errors that bring a sample into the quarantine could be due to the presence of some evasion techniques that we know are a limitation for static analysis. So that's the first point that might be noted as an interesting result to note. Okay, so in parallel with the pipeline development, we considered also another approach in order to help an analyst in interpret the result and assessing the reliability of the output of this pipeline. And it's unsupervised dimensionality reduction technique in order to compress, to reduce the feature space into 2 or 3D in order to be navigable and explorable. So that we can see there are some easy regions. This is a subset of the complete dataset, but just to give an idea. There are some easy regions where the classes are well separated and well clustered, and the classification here is easy. So if a sample falls into one of these clusters, we are relatively sure of the results. There are some outliers that might be the future vectors that we used are not enough to capture the characteristics and the functionality of this kind of samples, while there are some hard regions where we can see that the classes are not so well separated and the model here is most likely to fail. So if an analyst see that the sample that it was going through the pipeline falls in one of these hard regions, it might be it is an indication that that specific samples should require further investigation. And this is likely to be a limitation of the feature vectors that we used and this only static approach that we considered. Since, for example, if we consider only, instead of the AB class 2 output, we consider only the results of single engines from Aristotle. This is an example of the Kaspersky engine. We can see that even in this case, the same kind of mixing of the classes is present. We can see a cluster of packed malware. We can see that there are a lot of samples that are not even classified as malware, but are classified as benign. So this is a clear indication of the regions in the future space where further analysis or a more sophisticated algorithm should be used. So, in conclusion, we presented a first attempt, as we know of, a first attempt in the literature for a unique pipeline, a single pipeline for the complete taxonomic classification of malware. And we consider the first use of AV class true for the label extraction and a navigable atlas, let's call it like this, of the feature space for the result interpretation and quality assessment, let's say. So the next steps are, as I was saying, first of all, a multi-label approach, especially for the behavior classification. We know that a single sample can belong to many different classes. So the first expansion of the model is to consider a multi-label approach and extending the feature space with dynamic features or considering larger data set is if possible. And that is all for me. Thank you.
Thank you very much. Are there any questions for this presentation? Well, I have a question, but it is a comment rather than a question, actually.
Yes.
In this kind of experiments, the point is that if you use as an oracle the results of antiviruses services like VirusTotal, the point is that the labels for the same malware is not unique every time. So I think that if you choose as oracle, for instance, VirusTotal, and if you change the oracle and you use another threat intelligence platform or another threat intelligence classifier, the point is that the same malware can have different labels. So this can happen for the family. This happens for the family in general, but this can happen also for the behavior, because there is not a universal taxonomy that is shared by all these platforms. So I don't know if you think about this problem and you have already a solution, or you decided already for an approach to choose your oracle.
Okay, so yes, it's a legit comment, because it is well known that the labeling of malware it's a still standing problem. We don't have an absolute ground truth. But okay, there are two things I can say. The first one is why I wrote here improving label extraction through ML, in the sense that in the same spirit that as we do malware classification and as we do malware detection, we could think as the same approach to extract a unique nomenclature for the malware. Other than that, I mean, tools like AV class are interesting because they put a great effort into mapping different kind of names for different behaviors of different families into a common name. So even if two antivirus or two systems call the family in two different ways, this tool takes the keywords and as an internal lookup table for a common name of that. So the problem is mitigated by that, but it's not solved. So further analysis is for sure it's required, yes.
Thank you very much. There are no more questions, so we can skip to the next presenter. I ask Giuseppe Mario Malandrone to share his desktop and start.
Okay. Can you enable me the share content? Okay. Okay, can you see my slides?
Yes, we can.
Okay, now let's start. Good afternoon to everyone. My name is Giuseppe Mario Malandrone from Numera Sistemi e Informatica. My work is about PowerShell malware, and the title is PowerDecode, a PowerShell script decoder dedicated to malware analysis. In recent years, the most important anti-malware software companies identified a large number of attacks based on PowerShell. For example, Symantec in 2016 identified that attackers often use a technique called living off the land, which it consists on exploiting legitimate tool of the victim operative system for malicious purposes. Also in 2019, McAfee he highlighted that a 460% increase of PowerShell attacks compared to the previous year, and this increased further after in 2020 due to the pandemic. PowerShell is often used as attack vector for many reasons. One, you can run hidden commands, and we can perform shellcode injection or remote code execution. And since that the security setting has proven to be ineffective because it can be easily bypassed, and typically, attack based on PowerShell takes place with a huge spam mail campaign with malicious Office documents as attachments, and these attachments contains often some macros which can run PowerShell scripts in a hidden mode. So the goal is for the attacker to establish a connection to a command and control server. Another feature that is performed by attackers is code obfuscation. We can define code obfuscation as the alteration of the code syntax, which keeps the semantics of the code unchanged. On PowerShell, we can perform some types of obfuscation, which are classified in this way: string-based, encoded, compressed, base64, and randomization. The obfuscated code to be executed must be evaluated by the evaluation function, typically the invoke expression commandlet or a recursive call to PowerShell. About the actual state of art, we mention some related works, PowerDrive and PSDecode. These tools use some deobfuscation techniques to deobfuscate base64 format and invoke expression of commandlet overriding and regular expressions. However, this approach presents some limitation. For example, some problems are execution error applying commandlet overriding or syntax error introduced by regular expressions. Now let's start to present our tool, PowerDecode. PowerDecode is a PowerShell script decoder which can perform obfuscation layers removal, and it can perform also the malware activity report. It employs the same obfuscation techniques of the actual states of art, but it employs them in an innovative way, relying on accurate structure of obfuscated script described by a unary syntax tree. The operation scheme is showed in its diagram. We can see that the program take an obfuscate script, a text file as input, and as a cyclic algorithm remove all obfuscation layers. Specifically, the removal of base64 encoding is first recognized by two regular expressions, after is removed by an appropriate PowerShell method. To remove obfuscation layers containing vocal expression command let is performed command let overriding. This technique consists on execution of the script, of the obfuscated script, enabling some overriding, like invoke expression command let, which is overrided in such way to recompose string without convert them into statements. Also, further overrides are applied to intercept some malicious actions by the malware. This operation is repeated as long as syntax is correct. So in this way, we can extract some obfuscation layers. When all dependent obfuscation layers are removed, in the final stage of the obfuscation algorithm, regular expressions are performed to remove obfuscation which are not dependent on invoke expression command let. So, a generic script obfuscated across multiple layers can be easily described by a unary syntax tree model. In this model, a generic obfuscation layer is composed by an evaluation function which have as arguments a subblock of obfuscated code called C and some information about obfuscation, which is called D. The execution of the generic evaluation function f with these arguments generates the next layer. In the last layer, we have a not obfuscated code. An example of the obfuscation process of PowerDecode relying on the described model is shown here. We can see that in the starting layer, we have a base64 encoding. Now we have an evaluation function highlighted in red, which is the PowerShell call function. And we have in green a block of obfuscated code, and in yellow there are some information about obfuscation. The next layer recovered presents compressed format. In this case, the evaluation function is an obfuscated form of invoke expression. So we have in green a block of obfuscated code, and in yellow some obfuscation information about obfuscation. The achieved layer is analogous to the previous. We have an evaluation function which is an obfuscated invoke expression in a different form, but semantically it's the same. We have an obfuscated code in green, and in yellow some information about obfuscation. The last layer, finally, is the plain code, which presents no dependence by the command let invoke expression. PowerDecode was employed to solve many cases of obfuscated script received by VirusTotal. In this cases, the performance of the various tools of the state of art was compared with PowerDecode. We can see that PowerDecode was able to solve a wide range of obfuscations. About statistics, we can say that thanks the module to recognize obfuscation forms, we can carry out statistics about obfuscation employed by attackers. So regarding the invoke expression about command let overriding, PowerDecode was able to detect some action performed by malware and regard with carry out statistics. So we describe the limitation of pre-existing tools in comparison to PowerDecode. In this case, we consider PSDecode, a pre-existing tool, and we analyze a base64 obfuscated script. In this case, the file encoding was UTF-16, and PSDecode takes some difficulties to recognize the base64 format. For the same case, PowerDecode was able to solve this case because it employed the some regular expression to recognize base64 encoding. So it was able to solve this case. Another pre-existing tool was PowerDrive, and we can see that he had some problems solving this case of string-based obfuscation, which was very complex. So this tool generates a syntax error due to the high complexity of the script. Instead, for the same case, PowerDecode was able to solve all obfuscation layers. We can see now that it covered the layer 2 and 3, and after the layer 4, and finally in the layer 5, you can see the plain script. So it performs a malware analysis, and all URLs were extracted. Another flaw of the previous tool, PSDecode, was errors introduced by regular expression. This error was introduced when the tool tried to solve invoke expression dependent connect using regular expression. Due to the complexity of the script, this algorithm is not able to remove all obfuscation forms correctly. Instead, PowerDecode used commandlet invocation override to solve all obfuscation dependent on commandlet invoke expression. This strategy is successful because it was able to solve all these layers, and in an analog way to the previous example, in the last layer we can see the clear code, and it was performed also a malware analysis. In conclusion, we can see that there are infinite ways to obfuscate a script using PowerShell, but in the internet we can find a lot of customized obfuscators, but although these features, all obfuscation performable in PowerShell are classifiable. So regards PowerDecode, it can deobfuscate a wide range of scripts independently of syntactic complexity due to the implicit knowledge of the unary syntax tree. So PowerDecode can be easily integrated with complementary tools, and it is a very useful tool for malware analysis, in particular to detect malicious URL. And finally, we say that PowerDecode is online available as open source to software. So it's all. Thank you for your attention.
Thank you for the interesting proposal. I don't see any questions, so I have a question. Did you try your decoder on customized obfuscators on, I don't know, real malware? Because now the malware authors tend to use a lot customized obfuscators. So it could be very valuable if your tool is able to deobfuscate also customized obfuscators.
Okay, thank you for this question, Professor Visaggio. So PowerDecode was developed starting from an obfuscator, which is invoke obfuscation, developed by Daniel Bohannon. So it can solve a wide range of customized obfuscation, but in this case, to obfuscate malware, we can use the PowerShell framework. So we can can know that if you are wanting to obfuscate a script on PowerShell, you must use the PowerShell framework, and PowerDecode has this implicit knowledge. For example, if you want to obfuscate, to perform some kind of obfuscation, you can use the invoke expression commandlet on PowerShell, and PowerDecode is based off an invoke expression commandlet. The only limitation are all obfuscation which are not dependent on invoke expression. So in this case, it uses a regular expression and can remove certain types of obfuscation, but others cannot solve it. But this obfuscation with PowerDecode cannot resolve often are weak obfuscation types, and syntax, however, remains understandable.
Thank you very much.
Thank you.
Well, thank you again, and I call now the next presenter, who is Luca Cassano. Please, stage on you.
Okay, you should be able to listen to me and see the slides, isn't it? You can confirm?
Yeah, I do.
Okay. Thank you. So, thank you everybody. I am Luca Cassano. I am an assistant professor at the Politecnico di Milano. And we follow talking about software obfuscation. In particular, in this work, we exploit software obfuscation for hardware security. So, in particular, to protect microprocessors against hardware Trojans. This work in particular has been carried out by 3 of my students, which are Mattia, Tomas, and Alessandro, together with Dr. Giorgio Di Natale from Tima Laboratoire in Grenoble, France. A little bit of background. We know that the supply chain of integrated circuits is today extremely worldwide distributed. We have IP core providers, we have design teams spread around the world. The foundry is generally a third-party foundry. So there is a plethora of agents that cooperate to the design and fabrication of an integrated circuit. Of course, this distribution of the design process brought a dramatic decrease of the design time and cost, but also introduced possible threats in the design of integrated circuits. One of these threats is hardware Trojan. In a nutshell, what a hardware Trojan is, a hardware Trojan is an unwanted malicious modification of your circuit that stays silent, inactive most of the time, but then it is activated and does something wrong, something malicious in your circuit. This is a very general classical classification of hardware Trojans. We can classify hardware Trojans based on their physical characteristics. Based on their activation, we can have triggered hardware Trojans or always-on hardware Trojans. Hardware Trojans can be triggered internally by signals within the circuit or externally through signals that are received, for example, through the Wi-Fi antennas. And of course, we can classify hardware Trojans based on their payload, based on their activity. We have change functionality hardware Trojans, we have information stealing hardware Trojans, and then hardware Trojans that modify the specification of your circuit. In the very last years, also industry started concerning about hardware Trojans, because it has been demonstrated from these 3 papers that hardware Trojans that are called software exploitable hardware Trojans can be implanted into real-world microprocessors. So these Trojans are actually able to be, these are hardware modification of the microprocessor that can be activated via software, and that can, in the first case, allow the attacker to exploit an unwanted software, an unauthorized software in the operating system. And in the last two cases, the Trojan allows the attacker to gain unauthorized privileges, so become a root in the operating system. So this is a Trojan, I repeat, this is a Trojan in the hardware, in the microprocessor, that is exploited via software to gain privileges over the operating system. This research field has been active in the last 20 or 30 years. There is a plethora of techniques for detecting hardware Trojans before deployment, based on, for example, side channel analysis, formal verification, proof carrying hardware, testing, logic testing, optical inspection. Most of these techniques suffer from one or both these drawbacks. They often need a golden copy of the circuit, which is actually very rarely available. A golden copy means a secure, trustworthy copy of the circuit. And they often need to trigger the hardware Trojan at design time. But this means that if I'm able to trigger the hardware Trojan when I'm trying to detect the hardware Trojan, this is, of course, let's say, not that useful for my purposes. So a new paradigm raised in the last years, which is design for trust. So I do not want to detect the Trojan before deploying the system, but I want to deploy the system and I want to build a trusted system on top of untrusted components, or I want to run my software in a trusted environment, although the system is partially or totally untrusted. Most of the few techniques that specifically address microprocessors, so the design for trust techniques that specifically address microprocessors and hardware Trojans, rely on redundant components, redundant execution, or full duplication or triplication of the microprocessor. So there are 2 or 3 approaches in the literature that exploit either software redundancy or hardware redundancy, but they all rely on redundancy. They all rely on vendor diversity. So I need different copies of the circuit of the microprocessor, for example, belonging to different vendors. So they are all design time techniques that need special hardware. The only work that addresses software, so a software-based technique for defeating hardware Trojan, is this work from the Politecnico di Torino, from Ernesto Sanchez, that tries to exploit software obfuscation to defeat hardware Trojans. They only consider sequentially triggered and change functionality hardware Trojans, so a subset of the Trojans, and they only consider equivalent instruction substitution as a software manipulation technique. So what about our work? What we wanted to do is to exploit software, classical software manipulation, classical software obfuscation at the assembly level, to try to make life hard for hardware Trojans, in particular hardware Trojan that try to steal information from our microprocessor while the software is running. The considered hardware Trojans are either triggered or always on, and we considered hardware Trojans that work at the microarchitectural level. So hardware Trojans that are able to read the values within the registers and read the fetched instructions while the software is working. So we're not considering RTL or gate level Trojans. This is the framework we are proposing. We called it DETON. It takes the assembly code of the program under protection. It takes a configuration file that specifies how many times each module has to be run, and a description of the microprocessor in terms of the number of registers, the size of the registers, the names of the registers, then a CFG description of the software is built, and then iteratively we run garbage code insertion, constant obfuscation, and register scrambling in order to get a final obfuscated program. Going a little bit into the details of the techniques we implemented, what we mean for garbage code insertion, we just add garbage instructions, so useless instructions in random in random points within our code. On the left, you have a very simple example of a program that reads two variables and calculates the sum of the two variables. And so we just randomly select garbage instructions. They use unused registers in that specific point of the program in which we are adding the garbage code. And we do not add jump or div in order not to, let's say, drive our software into unwanted problematic conditions. What about constant obfuscation? We randomly select a constant in our code, and we build what we call an obfuscation chain, which is a sequence of instructions that are able, at the end of the execution, to leave the right value in the right register at the right moment. So the add I instruction here is substituted with this block of instructions here. So we are adding more instructions to calculate a constant. And finally, register scrambling means that in a specific point of our code, we scramble the content of the register. So in this case, for example, we are scrambling the content of the ASCII register in the T1 register. So we are using T1 instead of ASCII. So we are moving information around the registers in the microprocessor. What we measured, which are the metrics we measured. As an effectiveness metric, we defined the register hit, which is an inverse measure of the time elapsed since the last write in each register. So we are measuring how often a register is written. And as an efficiency measure, we calculated the program enlargement, which is the number of instructions that we added with respect to the original program. Here we are considering 6 software benchmarks. We considered a RISC-V microprocessor, an ARIAM5 version of the RISC-V microprocessor. Here I'm showing the average hit for all the 32 registers of the ARIAM5 for every benchmark in the plain and in the obfuscated versions of the software. We can see that in all cases, of course, the register hit is extremely higher in the obfuscated version with respect to the plain version, because we are actually using and writing much more registers during the execution of the software. If we zoom into, for example, in this case, the SHA benchmark, and we look at the average hit over the entire program execution for every register, we can see that in the plain version of the software, we just use 6 registers, while in the obfuscated version, we use more or less all the registers except the first 4 ones, and the register hit is more or less the same for every registers in the microprocessor. And then here we can see a complete, let's say, picture of the execution of the SHA program, because we are looking at every single instruction cycle and every single register. In the plain version on the left side and in the obfuscated version on the right side, we can see that we have much more register write spread around the entire execution of the SHA. So we are adding garbage data, and we are moving information in the registers. What about the overhead? Of course, the overhead is high, and is higher for the small benchmarks. We have to take into account that no design space exploration has been performed. So we do not tune the parameters of DETON. We just performed an example run. So of course, the execution of DETON can be tuned and optimized. And we have also to take into account that this approach, this technique, does not need any modification of the hardware. It's totally software, purely software. So just to conclude, we presented DETON, which is this framework for software manipulation, software obfuscation to protect microprocessor-based systems against information stealing hardware Trojans. What about future work? Of course, we plan to validate the metric, the register hit that we use for evaluating the effectiveness of DETON. So we want to correlate the values of the hit with the ability of the attacker to steal information from the microprocessor. And of course, we want to introduce some kind of design space exploration engine to optimize the execution of the DETON framework. That's all for my presentation. Thank you very much for your attention. Any question is totally welcome. Thank you.
Thank you very much, Luca. I don't see any questions, so I have a question for you. For the validation, the validation that you will perform later, do you have a set of hardware Trojans? Can you use a set of hardware Trojans?
Yeah, the problem is that there is only one, let's say, benchmark of hardware Trojans available, which has been developed by the group of Professor Teranipur from the Florida University, and they are all hardware Trojans. So they are circuit level hardware Trojans. The problem in this particular field is that there are no benchmarks. So yeah, we are trying to understand how to simulate the behavior, the functional behavior of the hardware Trojans, in order to be able to correlate the register hit with the amount of data that the microprocessor is exposing.
I see. Okay, good. Okay. So it could be a good idea to create another benchmark for hardware Trojans.
Yeah, it could be.
Okay, thank you very much. I don't see any questions, so we can go to the next presenter, who is Massimo Guarascio. Please.
Okay. Can you see my screen?
Yeah, we can.
Okay. Well, hello to everybody. I am Massimo Guarascio, and I am a researcher at the Institute for High Performance Computing and Networking. In this presentation, I'll introduce a framework for the mitigation of attack performed via digital images. Specifically, first I'll give a short introduction about the problem and the scenario. Then I'll define the solution approach adopted in our work, and finally I'll show the evaluation result on a real image dataset. Well, we can start. Our goal basically is the mitigation of malware targeting digital images. These attacks try to exfiltrate sensitive data and to distribute malicious code via information hiding techniques. The idea consists in exploiting image processing methods to recover corrupted images and simultaneously destroy embedded information and malicious code. So we defined a deep learning-based framework able to sanitize digital images by disrupting the hidden armor payload without degrading their quality. Okay. A bit of background. Stegomalware represents an emerging class of threats exploiting hidden communication paths. Basically, stenography and information hiding techniques are used to hide malware and to bypass security perimeters, so to make the detection hard. Several and different type of carriers, for example images, are used to leak relevant information and to hide malicious code. In the last year, different stenography techniques have been applied to these carriers. In particular, in our scenario, we focused on images and used a tool based on least significant bit technique. LS-bit stenography is a technique in which least significant bit of pixel of the image is replaced with data or malware bits. Okay. This is our scenario. The typical attack model adopted by a malware on digital image is shown in a figure. The goal of the attacker is evading detection mechanism, for example, antivirus, and allowing data exchange even in the presence of a firewall. The approach used by these attackers consists in exploiting information hiding based techniques to inject a secret information within the digital picture without generating visual artifacts, since the visual artifacts can reveal the presence of a malware. Our idea is adopting image processing techniques to reveal and or mitigate these attacks. This is our framework. The proposed solution can be thought as a middle box able to intercept data flow and process the images. The idea consists in deploying our image sanitizer module in a proxying architecture, only targeting specific protocols. For example, setting up a HTTP proxy to prevent an attacker to distribute malicious code via web page or content shared on social networks. As regards our methodology, the image sanitation task can be formalized as follows. Basically, let X the input image and epsilon a priori known malicious attack compromising the content of the image into X plus epsilon. We want to devise a neural functional N such that N of X plus epsilon can approximate X, while we ensure N of X can approximate X for uncompromised images. In figure, we can see the specific architecture. Basically, the architecture is loosely inspired to UNet and is a download encoder architecture where the input image is progressively halved in size and doubled in volume by means a stack of convolutional layer. The final latent representation is composed of 512 layers and with size 60 times 60. The decoding phase is composed of a series of deconvolutional layers. Each of them is combined with the corresponding encoded layer according to a residual block scheme. In particular, each layer is equipped with a ReLU activation function, except the last one. The last one is equipped with a sigmoid activation function. As regards the learning, I mean, the DNN is learned on a set of image pair where X represents the original, the legitimate image, while Y is the compromised input. The learning phase aims at optimizing the network weights by minimizing the reconstruction loss. In particular, we adopt the mean square error as a loss function, as it can measure the divergence at pixel level. Okay. As regards experimentation, to prove the effectiveness of our solution, we perform a preliminary experimentation on a publicly available dataset. This dataset consists of 500 legitimate images, and these legitimate images have been processed to embed 110 different PowerShell scripts. The resulting dataset is once again divided into train, test, and validation. The train set is composed of 12,000 images, including both legitimate images and corrupted one. The test set contains 2,500 images, and validation sets contains about 5,000 images. Okay, now we can see the experimental results. First of all, I'll show some qualitative results. In the first row of this slide, you can see an example with the original image, the corrupted one, and the sanitized one. In particular, we have an image depicting an animal with a complex background. We can see that our solution makes a readable script and simultaneously restore the quality of the image. In particular, in the second row, we show some relevant details of the images, and we can see how our architecture was able to restore, partially restore the quality of the original image. This is another example, in this case, on an image depicting a landscape, and also in this case, our architecture was able to modify the PowerShell script, so to make it unreadable, and to restore, partially restore the quality of the image. In this slide, I'll show some quantitative result. The table reports some summary statistic to quantify the effectiveness of the sanitization. In particular, we compared the original images included in the test set with the sanitized and corrupted version in terms of mean square and binary cross entropy loss. within the table, the second column represents the cumulative absolute difference on the whole test set, while the third column represents the average number of pixel distortion that can be perceived. We can see how the sanitization strategy allows to recover on average more than 35% of the compromised pixel. Okay. In conclusion, we proposed an approach exploiting an autoencoder architecture to sanitize digital picture containing injected PowerShell scripts. The performed experimentation demonstrates the effectiveness of our approach in disrupting embedded information while restore the original images. As a future work, we plan to quantify this degree of disruption for a script and to extend the framework for enabling the detection of malicious embedded scripts. Well, thank you for your attention. Any question is welcome.
Thank you, Massimo, for your presentation. I have a question. Is your solution able to deal with any kind of scripts, or do you think your solution can be generalizable in this meaning?
Yeah, thanks for your question. Basically, our architecture tries to reconstruct the images. However, it is important to have a data set with example of corrupted images with the different kind of scripts. However, it could be generalized to modify, to disrupt the different type of script. So yes, it could be.
So the same keeps for the technique used for doing the steganography. So I mean, if you change the steganography technique, I guess your solution is able to detect the injected script as usual.
Yeah. As future work, we are interested to extend the framework in order to identify the malicious script, the malicious code, since we think that the latent space in such a way was able also to embed information about the malware. Okay.
I see. Thank you very much. So we can give the floor to Fabrizio Cara for the next talk.
Yes, perfect. Okay, are you able to see my screen?
Yeah, we can.
Perfect. So, good evening to everybody. I'm Fabrizio Cara, and I am a PhD student in computer engineering at the University of Cagliari. And in the next few minutes, I will present our work entitled Constraints and Feasibility of Adversarial Sample Creation using the Android System API. So, what we know, looking at pretty much all the security reports in the wild, is that Android is the most used operating system in the market for mobile platforms, and therefore is also the most adopted one. For this reason, multiple efforts have been made to develop systems capable of detecting potentially harmful applications. And nowadays, a lot of these solutions employ machine learning-based systems. But previous work has extensively shown that these systems may be vulnerable to certain types of attacks, such as the evasion attack, which is the focus of this work. So our goal with this work is to highlight what injection strategies attackers have to create real-world evasive samples. Basically, an evasion attack consists of manipulating a malicious sample to mislead a classification and make the classifier identify that sample as a benign one. In this work, our injection strategy is based on adding Android system API calls in the bytecode of the Android malicious applications. For what concerns previous work, some of them performed transformations only in limited parts of the Android application, like the manifest. Others don't preserve the stability of the application, causing, for example, high rates of crashes. And pretty much all of them use Decoder as a classification system. In our proposal, we discussed the constraints and the feasibility to create evasive samples using only Android system API calls. And we've developed a basic implementation to create evasive samples. And we evaluate our system using a multi-class classification system. So our goal is to evaluate to what extent it is feasible to generate real-world Android adversarial samples. And to do so, the first concern is the inverse feature mapping problem, which consists of moving from a manipulated feature vector to a real-world sample. To create and evaluate our system, we followed some constraints. First of all, we had to find all the available transformations that can be done to the malicious samples between all of the Android system API calls. Another constraint is to keep the semantics preserved so that the adversarial sample works exactly as the original sample. The most difficult constraints to comply with is the plausibility to human inspection, also because there are no automatic tools and approaches to evaluate it. And finally, the robustness of the evasive sample, because the transformation that we perform to the malicious samples have to be resilient to processing. Practically, what we did is that we selected from the system API, Android system API, the Android documentation, we selected the system APIs following some rules. First of all, we gathered all the usable classes, the usable packages, and for each package, we took all the classes with callable methods. Using this approach, we've been able to cover between 55 and 61% of the packages, and 18 and 33% of the classes, depending on the packages. So now we have the calls that we can actually inject to the samples, and we implemented a system to perform the iteration to the malicious samples, and this system consists of 3 phases. The first one is the feature mapping phase, in which the malicious application is statically analyzed to extract its features. To do so, we listed all the system API calls that are actually inside the sample, inside the bytecode of the sample. Then these methods are counted and mapped to create a feature vector. In the attack phase, we manipulate the extracted feature vector using a mimicry or a random noise approach. For the mimicry case, we choose as a reference a unique benign feature vector. And for the random noise addition case, we generate a random noise vector. Finally, in the inverse feature mapping problem, the inverse feature mapping phase, we take the adversarial feature vector generated in the attack phase, and every feature which is not already in the malicious sample that we choose is mapped into its corresponding system API call to generate a list of instruction to add in the sample. And finally, we inject these Android calls inside the bytecode of the Android application, and we generate an invasive malware. So a malware that can actually be classified as a benign sample. So that was a high-level overview of the adversarial samples creation system. And in the next slide, I'll show you the experimental evaluations that we performed. For what concerns the setting of the evaluations, we use a set of about 39,000 samples, gathered from VirusTotal, Drebing, and Contagion. And our data set is composed of about 3,000 ransomware, 18,000 trusted applications, and almost 18,000 generic malware. As a detection system, we use a real-world detection system for Android application, which is a Refactoid, which uses as a feature set the cumulative list of system API packages. And it uses 3 detection classes, which are ransomware, trusted, and generic malware. As a classifier, we train a multi-layer perceptron neural network. And for what concerns the mimicry case, we use a trusted feature vector to manipulate the malicious feature vector. The goal is to create an adversarial feature vector for which the malware feature vector looks like the benign feature vector to the eyes of the classification system. This benign vector may be the mean or the median vector of all the trusted sample that we have, or the real feature vector closest to the mean or median vector. So the image shows the evasion rate with respect to the increasing percentage of modified features. And we can see that no matter what trusted sample as a reference we use, increasing the number of alterations means better evasion rates. For example, we have that modifying 40% of the features using the real mean trusted feature vector. There is an evasion rate that can be about 75%, which is a good result. In the case of the random noise attack, we evaluate 2 ways of generating the random noise feature vector. First one is the absolute case, in which n is the chosen maximum noise level that we want to add, and we increase each malicious feature with a random value between 0 and n. And in the figure, we still have the evasion rate with respect to the increasing percentage of modified features. And we can see that for different level of noise between 1 and 100%, the higher the modifications and the noise level are, the higher the evasion rate is. And taking the case of 40% of injected features and a noise level equal to 20%, we have an evasion rate of about 60%. The second way is the relative case. In this case, n% represents the maximum noise level with respect to the original number of the original value of that feature. So we increase each malicious feature with a random value between 0 and n% of the original value of that feature. As we can see in the image, in this case, the evasion rate is really low. This is because the majority of the features have a 0 value. So we actually performing a very low number of manipulations. Some considerations. The results of the mimicry and the random noise addition attack show that the evasion rates can go up around 80%. And while we attain high results of preserved semantics and robustness by design, the plausibility of the adversarial samples cannot be assured. And logically, we can say that the plausibility to human inspection is inversely correlated to the number of injected features. So more are the features that we injected, more easier it is to a human inspection to see and to actually get all the dead code that has been added. And so in the images, we evaluate the impact on the adversarial samples in terms of extra calls added. In the x-axis, we have the percentage of modified features. In the y-axis, we have the number of injected calls in percentage with the original value in black, and the number of absolute injected calls in yellow. As we can see, for the mimicry case, the one on the left, this case causes a massive increase in calls, while the random noise addition attack attains much better results in this sense. As we're considering the case of 40% of injected features, we have to add something like 10,000 calls for the mimicry case and something like 1,000 calls for the random noise addition. In conclusion, we presented a study about the feasibility of creating a system that is capable of generating adversarial sample through the injection of only Android system API calls. And this strategy may be particularly effective for creating a massive amount of adversarial samples with, let's say, a relatively low effort by the attackers. And the experimental results show that both mimicry and the random noise attacks are enough to evade the classification. However, using this approach doesn't comply with the constraints of plausibility and robustness. And that's because to avoid the classification, it is necessary to have a very high amount of system API calls, which means injecting a lot of that code. So we believe that future work should focus on using an approach that allows to minimize the number of injected features and to avoid the injection of that code that can be filtered out through flexible static analysis. So thank you for the attention.
Thank you, Fabrizio. I have a question. How do you think we can protect our perimeters from this kind of malware, this kind of adversarial samples, I mean?
Well, let's say that a way that we can defend our systems is using an adversarial approach to train the classification based on machine learning system. Because usually, in not all the cases, the classification system are trained with this kind of attacks in mind. And there are some ways to like using an adversary approach. So we say this classification can be evaded using this kind of attacks. So we train the classification system in such a way that that keeps this evasion attack or poisoning attack more difficult for an attacker to do. So the answer is using an adversary approach while we are training our classification system.
We have another question. Many apps and malware could implement anti-repackaging techniques. How have you analyzed that it is still installable and usable?
Well, it actually depends on the case. We didn't test our system with this kind of anti-repackaging case. And maybe that could be an idea to further investigate this system.
Okay, thank you very much, Fabrizio.
You're welcome.
Now we give the floor to the next presenter, who is Chinmay Siwak. I fear my pronunciation is not so good, so sorry for that.
That's fine.
Okay.
Okay. Can you see my screen?
Yes, it is not in presentation mode. Okay, full screen. Perfect. Yeah, go, please.
Okay. Yeah. Good evening, everybody. I'm Chinmay, and I'm PhD student at IMT Luca. I'll be presenting our work on enhancing malware classification with symbolic features. Starting with the motivation, we have three major motivations behind our work. That number one is ever-rising threat of a malware. And according to the recent statistics, the present-day malwares are responsible for at least 80% of the cyber attacks. Second, and the most important, is unsatisfactory behavioral analysis. I mean, what's the true behavior of a malware at first place is still not clear. The third one is unsatisfactory definitions of a malware. I mean, there is no well understood, agreed definition of a malware. And to answer these questions, I will be taking you through a working example of a malware family called Derushbi. It was introduced back in 2011 by a well-known APT group called Deep Panda. And the malicious behavior shown by this binary was basically disabling the security tools by turning off the Windows Defender and Windows Update service, and also the Windows Security Center service. And the APIs which were involved in such kind of a behavior were OpenSE Manager A, Open Service W, and Control Service. The OpenSE Manager A is basically an API which provides access to the service database. And Open Service W provides access to the service itself. And Control Service basically sends the control code to the service. Now let's see whether the traditional approaches which are based on APIs can deal with it. So we have a basic static analysis technique in which we inspect the program code, which requires no execution at all. And also it only takes into account a set of API invocations which appears in the code. And there is very little to get about the behavior of the malware itself from the API name, because these kind of sequences are also present in the benign-ware. The second approach is dynamic analysis, in which we require execution. We usually monitor the program execution under sandbox, and it only takes into account a single execution trace. So when we executed this malware, we didn't see any execution trace which involved this sequence of API and the behavior behind the sequence. Perhaps due to the insufficient execution time, or maybe the malware was able to detect the sandbox. But we have a technique which probably can enhance the malware classification and can encode this particular malicious behavior and such other behaviors of various samples. So here I'm introducing our methodology, which is basically based on symbolic execution, in which like it works like we replace the program values with the symbolic expressions denoting all the possible variable assignments. So it takes into account all the possible concrete executions, and we can fully explore the program code. But on the other hand, the full program exploration is still extremely highly computational, like it has a high computational cost. So in a nutshell, I want to say that the first phase of our technique is basically to encode the malicious behavior that I just introduced. So for that, we made a feature specification language called SFSL rules. So each rule is a triplet, which I will be explaining in our coming slides. The second phase is basically to explore the binary with the symbolic execution to match the target code with our SFSL rule. Third one is the feature vector which we are going to generate from the second phase. We are going to use it to train a malware machine learning classifier. So here we have a rule, which is a triplet, and triplet contains a declaration, path, and the Boolean predicate. Declaration is basically a pair of data type and the variable name. In this particular example, we have 5 integer variables and 1 string variable. In the path, path is a sequence of API calls, and each API call has assignment of variable depicting the return value in red, and we have a list of variables depicting the API parameters in black, and question mark depicts the argument which is immaterial for our analysis. The third one is Boolean predicate, which is basically defining the relationship between the API calls involved in a rule. So for example, in the OPSA manager A, we have a return value R in red. It is basically a service database, a pointer to a service database. And the first argument of open service W, which is D, is also a pointer to the service database. So these two are connected. So both of the APIs are invoked on the same service database. Then we have H and S. So S and H are basically the services. So S is a return value of open service W, which is basically a pointer to a service, and H is also the pointer to the service, which is the first argument of the control service API. So both of them are being invoked on the same service. And E here is basically the name of the service itself. It could be Windows Defend or Windows Update Service or any other security services. And G is the control code, which is sent by the control service API. Now here is the function call graph of the sample under investigation. In the red box, you can clearly see this particular function had a snippet of code which involved these 3 APIs, which was responsible for disabling the security tools. And you can clearly see this particular function is present deep inside the binary. So it was quite possible that the dynamic execution was not able to deal with such a behavior. Now I'll be explaining our symbolic feature extraction technique. And we start from the first instruction. Before starting, the initial symbolic state is basically an empty state. When we reach the first instruction, which is basically an API called OpenSC Manager, which I already introduced. When we execute this API, it returns an unconstrained value because we don't have the implementation of this API. It is treated purely as symbolic function. And then the constraints are added. So in this case, we still have the empty state. The first 2 arguments of the OpenSC Manager A are null, which basically means that it gives access to the system services. The third argument is generic execute. So it provides access to the privileges. And then we move on to the execution. Since this is an API call, so we are binding the feature variable, which is R, with the state variable called service DB. And it is depicted in a red box in brown. It is basically binding both the variables since service DB is a return value handled to the service database, which provides access to open service API to various kinds of services. Then the execution moves to the instruction, which is basically an if statement. It's a branching transition. And if the guard is true in this case, the program execution jumps to another location. But if it's false, then we move on to the next instruction. But before moving, this particular constraint is added to our state which is sigma 1, and we get the resulting state, which is sigma 2. Now we get to the second API in our path, which is Open Service W. Again, this is a call to an API, and it is treated purely as symbolic function. So the symbolic state snapshot is still the same, but since it is another program location, so the depiction of the symbolic state changed to sigma 3. Now after the execution, since it is an API call, we have to add the bindings to our symbolic state. And this binding is basically, again, a feature variable with the state variable. The feature variable and the state variable bindings are depicted in brown in the red box. All of them are basically the arguments and the return value of this particular API depicted in our rule. Then the execution moves to the next instruction, which is a if statement again. But this time, the guard, if it's true, then we move forward to the control service API. And before moving, we add constraint, which is service not equals 0. And then we move to the next instruction. The next instruction is control service API, which is the last and the final API invocation in our rule set. So again, it is treated as a fully symbolic function, and we get an unconstrained return value. So the symbolic state is still the same, but then we bind the feature variable with our state variables, and the final resulting symbolic state is sigma 5. So at the end of this symbolic execution of the program, we get the standard constraints, which are depicted in black, and the bindings, which are depicted in brown, and also the Boolean predicate, which was basically defining the relationship between the invocations present in our rule. Then these constraints are given to the SMT solver, which look for appropriate input values for the parameters that can make this expression hold true. So the SMT solver solution would look like something in the red box where the values for RD and service DB are equivalent to 1, and the values for SH and service are equivalent to 2, and G is equals to 1, which means that basically the control code is service stop, and E is win defend. So it is basically a service, security service, which these constraints satisfy. And the pointer, again, we have pointer plus 20. So in the previous slides, you can see in the brown that we have pointer plus 20. So basically E is equivalent to win defend. Now going into the data set, we basically have 32-bit portable executable samples, almost 2,200 of them, and basically we have samples from various APT groups and also from the targeted cyber attacks like Dark Hotel and Gordon Group. And as far as the benign samples are concerned, we took 81% of them from a well-known book called Malware Data Science, and 19% were taken from some other sources. As far as the preliminary results are concerned, the decision tree and the random forest classifiers performed better than all of them. But the good thing about these preliminary results were accuracies were still above 80%, and logistic regression, which gives us a very simple decision boundary, performed well as compared to the other classifiers, despite having a very simple decision boundary, which means that our features are strong enough to classify the samples. As far as the ROC curves are concerned, again, the decision tree and the random forest were above all of them. but logistic regression was also not far behind. In conclusion, I would like to say that we presented a novel feature specification language to encode the malicious behavior of any sample, which is known as SFSL. Secondly, we developed a prototype of our approach by combining the symbolic feature extraction technique with the machine learning classifier. And the preliminary results are quite encouraging, and we would like to expand this work further. In future work, we also plan to perform zero-day malware detection by splitting the data set according to year in which the malware was discovered. So this needs to be done, and data set also needs to be expanded. Thank you very much. And now I am open for the questions.
Thank you very much, Chinmay. I have a question. How do you think the accuracy can be improved, perhaps by using some deep learning classifier, or do you think to use another strategy?
Well, thanks for that question. Yeah, it can be improved by deep learning classifiers also, but initially we were focusing on expanding the number of the features. So once we increase the features and the data set, we would like to see the results on deep learning algos also, certainly.
I see. Okay, thank you very much. We are a little bit late, so I suddenly give the floor to the last presenter, Vincenzo, please.
Hi, I will present quickly. Don't worry.
Oh, no, thank you. But take your time. Take your time. Don't worry.